Good afternoon and welcome to Open Systems Media Automotive Technologies Virtual Conference, produced by the group at Embedded Computing Design. My name is Rich Nass and I will be your moderator for this presentation. I'm also the Executive Vice President of Open Systems Media. I lead the embedded and IoT teams for Embedded Computing Design. That is not my name that you're seeing on that slide. That is of the speaker. That is actually my very messy office that you're seeing in the video. We are live today. So if there's an issue, you'll know it's because we are live. But so far, so good. This is actually the third of three, and I'll go through that in just a second. This conference is made possible thanks to our sponsors, those being Qorvo, IAR Systems, Texas Instruments, AD-Link Technologies, and Imagination Technologies. As I said, this is the third of three live presentations. Earlier this morning, we heard from Sean Prestridge of IAR Systems, and he spoke about the ISO 26262 certification process. And then just a little while ago, we heard from Daniel Torres of Texas Instruments, who led a discussion about the battery management system that would reside within an automobile. Both of those presentations are now available in an on-demand version, so I encourage you to check them out. In between those and before that and after that and anytime after this, you can see any of the presentations that were pre-recorded before the event. There's more than a dozen of them, and they fall into any of the five categories, which would be ADAS, autonomous drive, electric vehicles and powertrain, in-vehicle infotainment, and safety and security. All really good stuff with a lot of information for designers, developers. So please check them out when you can. But let's get to the topic at hand, where we will be covering the V2X Spectrum Coexistence challenges that are presented by autonomous vehicles. This presentation will be delivered by Ali Bawangaonwala of Qorvo. You can see Ali's bio up on your display. I won't read it for you, as you can do that yourself. Before Ali starts, let me go over some of the housekeeping items very quickly. His presentation will take about 45 minutes, and that'll leave us some time to answer your questions. We will answer as many as time permits. We tend to answer them in chronological order, so ask them as you think of them. Don't wait until the presentation's over, otherwise we may not have a chance to get to it. If we do not have a chance to answer your question as part of the presentation, somebody from Qorvo will get back to you after we're done, most likely by email, but you will get an answer at some point. You'll find on your console window where there's a box where you can ask those questions in real time, so ask them right away. If you have an issue with the console itself, like if the audio doesn't sound right or the slides are not advancing, put that question into the question box and one of our technicians will get back to you with a solution. There's a maximize button on there that allows you to see the slides in a larger window. And one of those buttons down at the bottom will let you download the slides that Ali is delivering. So if you click on that, you can follow along with the slides. You can print them out or do whatever you want with them. Okay, enough from me. Let's bring out Ali to start the presentation. Ali, take it away.
All right. Thanks for the introduction. Appreciate it. Let me share my screen real quick, and then we can get started. All right. And that
Looks good, Ali. You're good to go.
All right. Thank you very much. Appreciate the introduction. So hello, everyone. My name is Ali, and I am the head of marketing for V2X at Qorvo. The topic of today's discussion does not focus on sensors and cameras or the underlying software and computations required to make autonomous driving a reality. We will also not be focusing on the safety and convenience use cases of autonomous driving. What this discussion today will be focused mainly on the radio frequency or the RF aspects related to the electronics and hardware, which make connectivity a reality. So from an agenda standpoint, we'll take a look at the trends in automotive, and then we will dive into the coexistence challenges, mainly associated with the RF electronics on board, the V2X radio and the Wi-Fi system, the Wi-Fi and the LTE and V2X with electronic toll collection. So here are the biggest trends in automotive. One is electrification. I mean, in today's presentation, we already heard about electrification and battery management, and this is one of the key topics. You will continue to see more and more electric cars with improved mileage per charge. OEMs are investing billions of dollars in battery technology to make electric cars a reality. Connectivity. So, connectivity is the heart of everything. People want to be connected all the time. Now more than ever, customers want a seamless connectivity experience. And not just connection via mobile phone or at home or in the office, but in their vehicles as well. Drivers can stay connected to their favorite apps, music, and entertainment. Kids can stay connected to their favorite games, or they can even get a jump on their homework on their way back home from school. Now imagine if you didn't have to stop into your local mechanic shop every time the check engine light in your car turned on. Well, in the future, you may not have to, thanks to the always on connectivity. Using remote access, manufacturers will be able to provide technology updates, safety updates, recall information, just like magic, without you ever needing to go to the repair shop with remote updates. Another big topic of discussion these days is autonomous driving, ADAS. Again, a lot of presentations on that topic, even in today's session. So this session here is going to focus on different aspects of autonomous driving. This topic is a presentation in itself, but at the high level today, we will focus on connectivity issues related to autonomous driving. So take a look at today's car versus a futuristic car. Today's car, it has a navigation system. Most cars have a default satellite radio for entertainment purposes, a Bluetooth, an MP3 player, a mobile integration platform. All these are table stakes these days. Well, what the car in the future will look like? It'll be self-driving for sure, with cellular and Wi-Fi connectivity, cameras, sensors, LiDAR, and all those advanced electronics which will make this car a connected, fully autonomous driving car. Well, in order for all this connectivity to become a reality, the automobile will have to be equipped with lots of radios. Mid to high-end cars are projected to have 4 to 5 radios built in to enable 4G LTE and 5G cellular connectivity, Wi-Fi telematics and infotainment for enhanced user experience, an SDARS radio for entertainment, GNSS for high-definition mapping, and a V2X radio to connect cars to everything around them and more. To make things even more exciting, all these radios need to be operable concurrently to provide a seamless user experience and passenger safety. This webinar focuses on some of the challenges associated with car connectivity in order for these radios to coexist together, and how can these be addressed with our unique filter solutions. So, before we get started, let's take a quick look as to what is V2X. V2X stands for Vehicle to Everything. And here is a graphic which shows the vision of vehicle connectivity, with cars talking to each other and everything around them. There is V2V, that is the vehicle to vehicle connectivity. There is also vehicle to infrastructure, that means car connected to traffic lights and all that infrastructure around it. Or the vehicle to network, which means the car would be connected to AT&T or the Verizon towers. And of course, vehicle to pedestrians to make sure that we can all coexist together safely. So at the high level, that is V2X, and now we're going to talk about what are the coexistence challenges associated with it, and more importantly, how we can address them, how we can mitigate those. So before we dive into all of that, let's take a look at why that performance matters. These are only some of the use cases that I'm showing here. There are a lot more. And these are safety related use cases. I think the day one use cases are non-safety related stuff. The advanced use cases are the ones that I'm showing here, is where you have car interaction with the road users, or the VRUs we call them. A blind turn warning is another interesting one. If you have a self-driving car, you want to make sure that all that is done. There is basically no room for error, and that's why the performance of the V2X link is so very important. Because again, remember, the purpose of the V2X radio is to enable connectivity between the cars and everything around them. It'll improve the overall traffic flow and safety and prevent accidents on the road by signaling critical time-sensitive information to other cars. And a desense on the V2X receiver could impact that communication between the cars and impact the critical use cases like self-braking, which could ultimately impact passenger safety. So that said, that kind of paves the way into the discussion, really, which is a core focus of this webinar. One of the first challenges I like to talk about is the V2X radio coexistence challenge with the 5 gigahertz Wi-Fi system. Now, as you can see here on the spectrum, this is a spectrum of the unibands. The unibands are the 5 gigahertz Wi-Fi spectrum, Uni 1, 2, and then Uni 3 bands right here, which are mainly comprise the 5.2 and the 5.6 gigahertz Wi-Fi spectrum. Sitting right next to the Wi-Fi spectrum is a V2X spectrum. For the US and for China, this spectrum is located right here at the high end of the band. But for Europe, full 5855 to 5925 gigahertz or megahertz is being discussed today. Fortunately or unfortunately, this spectrum is sitting right here next to the unibands. And in order to have a reliable V2X link, one would need a brick wall filter to guard the V2X spectrum in order to provide enough or adequate rejection to the near-band Wi-Fi signals. The second problem with the way the spectrum here is stacked up is that the mixing of the uni products creates noise. And this noise, unfortunately, falls right into the V2X spectrum. And once this noise makes its way into the V2X spectrum, there is no way to take it out. So again, just to summarize, there are two problems here. One is the adjacent channel interference, and second is the in-band noise, which is created by the mixing of the uni products. And Wi-Fi, just for table stakes, Wi-Fi interference could be coming from two sources. One is the in-car built-in Wi-Fi, the car that is the system that is retrofitted inside the car, the infotainment and the telematics. The second source of descent could be from a passenger hotspot. What if you had a passenger sitting somewhere in the car and turning on a mobile hotspot, and it happens to be a 5 gigahertz signal? That could interfere or that could interact with the V2X antenna as well, causing system issues. So when system designers are looking at coexistence, let's make sure we ensure that we want to ensure that it's taking care of both the issues, not just the Wi-Fi antenna to V2X antenna, but also the mobile hotspot, which is a big variable. All right. So the important thing is, what can we do about it? Well, there would be two types of filters needed in the system. One is to address the near-band attenuation issue that I talked about earlier, and to show what is the impact of not having a filter like that. Here's a comparison plot, which shows on the y-axis, it's showing the link distance. The plot to the left is the y-axis is the link distance, the V2X link distance, the connectivity, the link distance between the two cars, right? On the x-axis, it is the antenna coupling. This is the V2X to Wi-Fi antenna coupling. And this is a function of the V2X link distance is a function of the coupling mechanism between the two antennas. And what I'm showing here is a V2X system where you have a V2X TCU, telematics control unit, and connected by a coax cable. And this is the active antenna, the V2X portion in the active antenna. And if you were to not use the filters, in order to establish about 1,000 meters of link distance, you would need 80 dB of antenna isolation. This is according to our system calculator, okay? Let's say, hypothetically, you don't need 1,000 meters. You only need 200 or 300 meters, which would still be about here. You would still need about 70 dB isolation between the V2X and the Wi-Fi antennas in order to guarantee 200 to 300 meters of link distance. This is without using any filtering. Now, if you were to use a V2X coexistence filter, a nicely designed bandpass filter, which provides adequate attenuation to the nearby unichannels, and if you were to place this filter both on the TCU side and on the active antenna side, you could achieve 1,000 meters of link distance with only like 15-20 dB of isolation between the V2X and the Wi-Fi antennas. Now, there is a possibility that you don't need 1,000 meters. Let's say you're targeting only 200 or 300 meters. Well, even in that case, you could depopulate one of the filters from either the TCU or the active antennas. However, according to our system analysis, we recommend that if you were to choose a filter placement in a system, again, it's a function of how much isolation you have between the V2X and the Wi-Fi antennas. You want to choose the filter on the active antenna side. Okay. Now, here is another way of looking at things. So this is a situation I'm showing where you're seeing the sensitivity of the V2X system, and the dependency is on the antenna isolation. And there are 4 different cases I'm going to show here. One is where you have the filter both on the TCU and the active antenna side. The second case is when you have the filter just on the active antenna. The third case is where you have the filter just on the TCU in the telematics control unit and no filter. So as you can see in the table here, if you were to have a filter both in the TCU and in the active antenna, you could achieve good level of sensitivities, V2X sensitivity, even with up to 24 dB of isolation between the antennas. If you were to depopulate one of the filters, and let's say if you were to stick with only the active antenna, you would still need about 35 dB of isolation between the V2X and Wi-Fi antennas. If you had a filter on the TCU side, you would need about 60-65 dB of antenna isolation to achieve decent level or acceptable level of V2X sensitivity, enough for you to establish a reliable link, a V2X link. Now, of course, if you did not use a filter, you would want to guarantee at least 70-75 dB of isolation between the V2X and Wi-Fi antennas in order to guarantee a good level of sensitivity, acceptable level to establish a reliable link. So as you can see from both the slides, the link distance versus antenna isolation, and here sensitivity versus antenna isolation, directionally, you are getting the answer you want to hear. It's very important to take this into account in your system calculations, because no two antenna might be similar. Every automobile manufacturer might have different types of antennas with placement mechanisms and isolations. So you want to, each case is different. You want to make sure you're making decisions with data and good level of system analysis. So where would a filter like this sit in the system? What I'm showing here is a V2X system architecture. This is the CV2X or DSRC chipset, and I'm showing a dual active lineup, dual active antenna lineup. If you had a single active system, then you would have only one lineup right here and one passive. But in this case, it's a dual active case. So the flow is coming out of the chipset, going into the V2X FEM, And this is the Coexist filter I'm talking about. This is the QPQ 2200Q. This is a V2X to Wi-Fi coexist filter that enables the coexistence between the two systems. And we recommend that we place this filter on the receive path. Coming out of the V2X, this is the telematics side of things. Coming out of the telematics TCU, you go through a coax cable. The length of the coax cable, the loss in the system, the loss over here will be dependent on the length of the coax cable and, of course, the quality of the coax cable. The power here needs to be compensated. The loss in power here needs to be compensated for, and that's why you have the active antenna, active compensation circuitry right here, going through a digital step attenuator, going through a V2X FEM, and out through the antenna. Now, again, on the active antenna side, we recommend that this filter is placed on the receive path as shown. And of course, in this system, I'm showing two coexist filters. That means it provides the optimal level of reliability when it comes to the V2X communication. Now, notice that there is a filter right here on the antenna. This is also a bandpass filter, but this filter is different from the V2X Coexist filter. In my interaction with my customers, some customers tell me that they do already have a filter like this, and this bandpass filter is good enough. Well, not exactly, because this is a bandpass filter, agreed. However, the purpose of this bandpass filter is to protect the system from reverse harmonics. This is actually a roofing filter, a low insertion loss roofing filter. It has nothing to do with V2X to Wi-Fi coexistence. And to prove my point, I can show you on a slide here as to what this is. What you're seeing here, I would like to draw your attention to the center plot, where I'm showing comparison of the blue trace is the QPQ 2200Q V2X to Wi-Fi coexist filter. The black trace is the roofing filter. And as you can see, the QPQ 2200Q filter provides this level of attenuation, more than 40 dB, 35-40 dB of attenuation to the unibands, while providing low insertion loss for the V2X. So this is fundamentally a very different filter, and you can't replace one for the other. Now, what you could do is, going back to the system, what you could do is, if your link budget allows, you could place this filter over here at the antenna. Then you don't need to have another filter like this, because this filter will do both the jobs. It will protect the system from the reverse harmonics and enable coexistence. However, I want to make sure you understand that this is a low insertion loss filter, roofing filter. The coexist filter has slightly higher insertion loss. And that's mainly because it has to roll off quickly, and the band edges, the insertion loss of the band edges of this filter would be slightly worse compared to the roofing filter in order to provide the level of attenuation it does. Now, zooming into the V2X compensator, I just want to make sure that the previous system architecture is somewhat high level. This is more detailed view of the V2X compensator. And the signal coming in here is from the telematics control unit, coming through the cable loss. Like I mentioned earlier, the loss here could be anywhere from 5 to 15 dB, and that would be the loss you want to, that is what you want to compensate in this unit right here. The signal comes in, would go through a Xplexer and a bias T, which is connected to the MCU. The RF is sliced out and goes through a step attenuator, a digital step attenuator. The signal then will go through a fast switching TX RX switch. The TX portion goes through a gain block. Now, again, the need for the gain block will be totally dependent on the amount of power you're trying to compensate for. That'll be dependent on the loss you would have here. In some systems, maybe you don't need the gain block. You can go directly into the V2X FEM. However, we are showing an optional circuitry here. It could either be bypassed or you may not need it at all. It totally depends on your link budget. The signal goes out through the antenna, coming back in on the receive path, as you can see, it goes through a coexist filter and possibly a first stage of amplification for the LNA, and then going back into the system for the second stage. And again, the need for this first stage LNA will be dependent on your system calculations and what you're trying to achieve. What I'm showing here is what we have developed at Qorvo. We have a systems board which shows all these components that I'm highlighted in blue right here, 1, 2, 3, 4, 5, 6 components. And you get to see that they've been laid out optimally and matched just to demonstrate the RF performance that you can achieve with these components. All of these components I'm showing here in blue are in mass production, and they're all AEC-Q grade 2 qualified. So remember on the spectrum slide, the first slide I showed, I talked about two different problems. One was the adjacent channel interference, and so far we have looked at the bandpass filter to protect the V2X system. The second type of filter that would be needed is to extract the noise which is produced due to the mixing of the uni products. The uni products, it's basically the 5 GHz signals. So what I'm showing here is a block diagram of a 2x2 MIMO dual band Wi-Fi system. And this is the 5 GHz FEM, dual FEM, and the output of this FEM is what could have the noise that could potentially impact the V2X performance if the noise made its way into the V2X system. Now, what I'm showing here to the right is a system calculator output, which is showing a V2X front end. Again, the same diagram like I showed earlier. This is your TCU coming out, going into the active antenna. And I'm showing a bandpass filter here. This is a V2X Coexist filter. But again, this has nothing to do with this problem. This is a different filter to enable Wi-Fi coexistence. We are talking about noise that is coming out of the Wi-Fi system, which could, if it radiated out through this Wi-Fi antenna, could couple back in through the V2X antenna and will show up in the V2X system. And that is in band. So you can't take it out with a bandpass filter. So one way to solve this problem is put a notch filter at the output of the 5 GHz FEM. And this is the approach Qorvo is taking today. We have designed a notch filter that notches out the V2X noise and provides low insertion loss or passband for the Wi-Fi signals, for the 5.2, 5.6 GHz Wi-Fi signal. If you didn't do that, you could see descents on the V2X receiver up to 1820 dB, which will impair the performance of the V2X receiver. That means your connection with the V2X system could be impaired. However, if you were to place a notch filter in the V2X system, in the Wi-Fi system at the output of the 5 GHz FEM, you could eliminate the descents for the most part. And I have another slide that shows that provides more details on how this works, or the level of isolation that you need between the two antennas to guarantee good level of sensitivity. So here's the same diagram, the dual band Wi-Fi system, 2x2 MIMO system. And the table now, what I'm showing here is V2X to Wi-Fi antenna isolation is my first column. And to the right, what you're seeing in the 3 columns is the descents to the V2X receiver caused by the noise. And there are 3 situations I'm showing here. One is no V2X notch. Second is the V2X notch placed after the PA. And the third one is the V2X notch placed before the PA. That means between the chipset and the Wi-Fi FEM. So let's take a look at the first case. If you did not have a V2X notch, what I'm showing here, according to our system calculator, you would need about 65 dB of isolation between the V2X and the Wi-Fi antennas in order to guarantee good level of sensitivity of the V2X receiver. On the other hand, if you did place a notch filter at the output of the V2X FEM, you could get by with just about 30 dB of isolation. Alternatively, you could place a notch filter at the input of the V2X FEM, on the input of the Wi-Fi FEM, because just in case there could be cases where you can't deal with the insertion loss provided with this notch filter to the Wi-Fi system, so you could place this before the pre-PA. In that case, you would need to guarantee about 30-35 dB of isolation of V2X to Wi-Fi antenna isolation in order to achieve decent level of sensitivity. So as you can see, it's really directionally, it's giving you the answer. The system block diagram shows with and without notch filter what happens. But then the next question could be that what is the scale of antenna isolation we are dealing with? And I think this table gives you that level of information as to what happens, what if you had 45 dB of isolation, or what if you had 35 dB of isolation. So I think this is a very nifty calculator that gives you that level of detail. So to wrap it up, we talked about V2X for V2X to Wi-Fi, two different filters. One is a bandpass filter, second is a notch filter. If your V2X and Wi-Fi antennas are close by and you can't provide adequate amount of isolation, you may need one or the other or both the filters to fully mitigate any connectivity issues. All right, so the second type of coexistence challenge, this is a well-known coexistence, the 2.4 gigahertz Wi-Fi coexistence with the LTE bands 47 and band 41. This is a well-known issue on the mobile handsets. Almost every single mobile handset I know of uses a 2.4 gigahertz filter to enable coexistence with the other LTE bands. And as can be seen from the frequency spectrum, this is the 2.4 gigahertz spectrum right here. On the left side, you have the band 40, and the right side, you have band 7 and band 41. And the purpose of this filter is to provide adequate attenuation to band 40, band 7, band 41, while providing low insertion loss for the 2.4 gigahertz system. Again, this is the dual band 2x2 MIMO Wi-Fi system, and the filter you would need to enable coexistence would be a filter like this shown right here at the output of the 2.4 gigahertz FEM. Okay. So just to break away from the monotony of the discussion of the coexistence, I thought this is pretty interesting. I mean, this is something about the evolution of the facts I collected, and I thought I would like to share this with you. So I find it pretty intriguing that the first true technological leap forward for cars came in 1911, when automobile companies began installing the electric starters into the vehicles. The cigarette lighter arrived in 1925, and the radio in 1930. The power steering came only in 1956, and the 9-track player in 1965, with the cassette deck, which is arcane. Really, it came out in 1970, and it was pretty cool back in the day. At least I have driven cars. I bought a 2002 Nissan Maxima and then back in early 2000. It has a 6 CD changer with a cassette player, and it was state of art. It felt like I had everything. But when I look back 18 years ago, I mean, and the cars that we drive today, it's very different, very technologically advanced, very different cars. In fact, I still have that Nissan Maxima, and that is the only car I have where I can play a cassette. Not that I play cassettes, but that's only, at least my kids, I can show it to them and say, this is a cassette player. This is how the cassette player looked like. Anyway, moving on, the true driver conveniences started rolling in after that. The compact displays, like I said, started popping up as early as 1985, followed by dashboard computer diagnostics in 1994, the GPS nav systems in 1995, and then in the 2000s, the car began featuring USB ports and the Bluetooth connectivity, the latter of which was a true precursor to connected cars of today. All right, so going back to the V2X coexistence challenge, another important coexistence issue I'd like to discuss today is the V2X with electronic toll collection. So what is electronic toll collection? Well, as the name states, it is a radio that sits in the car and enables seamless toll transaction whenever the car approaches the toll booth. Today's tolling systems are mapping-based devices. That means the coordinates where the tolling systems are indicated by the mapping software, which wakes up the ETC receiver, and whenever it passes the toll booth, it does the tolling transaction. So it's mapping dependent. And so far, that was okay. However, moving forward, that may not be okay. And that's because of V2X, and I'll show you in a minute why that is a problem. So the coexistence here between V2X and ETC can be solved by two ways. One is through software mitigation methods, and that is not what we're going to talk about today. What we are going to focus on is the hardware mitigation method. So this is a problem. This is a spectrum coexistence challenge between ETC and V2X. What I'm showing here is a spectrum of Europe and for China for ETC and V2X. It is not an issue for North America because the ETC spectrum for North America is nowhere close to the V2X spectrum. But for Europe, it is 5795 to 5815, as can be seen here, with a 40 megahertz gap. And then this is a V2X spectrum. This is 5855 to 5925 for Europe. For China, the ETC spectrum is non-contiguous. You have the 10 megahertz uplink, 10 megahertz downlink, close by to very similar frequency ranges, but not exactly the same. It's just spaced out like this. Then you have a 65 megahertz gap, and then this is the V2X spectrum, the upper 20 megahertz of the V2X for Europe. And for North America as well, this is the upper 20 megahertz for now. So the problem here is that even though the gap is 40 and 65 megahertz, which may seem like a lot, this is not exactly a lot, and I'll show you in a minute why this is a problem. So if you look at this slide here's a spectrum emissions plot of the V2X system. Okay, this is not the ETC, this is a V2X system spectrum emissions plot, and this is centered for Europe. This is centered at the low end of the spectrum, of the V2X spectrum. And what you're seeing here is the spectrum power on the y-axis. The input signal is in green, the output signal is in blue, and then I have a marker for the ETC spec. And as you can see, if we didn't do anything about it, the power from the V2X system will completely overload or overdrive the ETC receiver. That means the ETC receiver will not be visible, and you will not be able to do a toll transaction unless you do something about it. So the plot to the right is where we have inserted a carefully designed notch filter, which notches out the ETC spectrum before it gets amplified by the V2X FEM. And if you were to insert a filter like this, you can see that the output of the V2X FEM, which is falling in the ETC band, is below the ETC spec line item, which means that you can coexist. It's passing the ETC spec. We did a similar analysis for China use case as well. As you can see from the plot on the left-hand side, the ETC spec from the V2X system, and again, this is centered at the low end of the China spectrum for V2X. And as you can see, the system really cannot coexist until you place a notch filter. This is a different type of notch filter because you remember the China spectrum is slightly different compared to the Europe spectrum. But if you did that, you can see the two systems can actually coexist together. So it's very important to understand, it's first of all, there are two different systems for Europe and for China. It's not exactly the same filter. However, the important question is that where do you place this filter exactly? And this is the V2X system architecture, where I'm showing, if you remember, I showed earlier the dual active case. This is a same system that I'm showing. The only thing here is I have added the ETC notch filters. For the dual active, let's assume for a moment that you have a dual active case. You would need a pair of notch filters between the chipset and the V2X FEM. Now you could place this pair of filters either on the TCU side, or you could place it on the active antenna. You don't need the filters on both sides though. You definitely don't need this filter. It'll be an overkill, but again, it depends. It depends on your system. If our recommendation, according to our system analysis, is that you would want to place a filter on the TCU side. However, you have degrees of freedom to place it on the active antenna side as well. So to wrap up, it's important to ask the right questions. If you are designing, we have worked with OEMs, we have worked with multiple module makers, we have worked with active antenna suppliers, and what we have learned is that in the automotive ecosystem, you have, of course, the OEM dictating their requirements, but then there are different module makers in play. It's not one company making the TCU and the NAD and the Wi-Fi module and the V2X and the active antenna. It's not by one company. It's multiple suppliers doing different pieces of the puzzle. And if you are a system designer, you want to make sure that you're asking the right question. So I thought I will develop a chart like this, a flow chart like this will help you ask the right questions to enable you to decide whether your system needs to be designed to coexist with other systems or not. And just to walk you through it, the first question to be asked is, obviously, what system is being designed? If this is a V2X TCU and the active antenna system, the question that you want to ask is, if you are a designer for the V2X system, let's say for the TCU and the active antenna, or one or the other, the first question you should be asking is, does the V2X system need to coexist with the 5 GHz Wi-Fi? Because you may assume that you are designing the best-in-class V2X system, but not knowing if you are going to coexist with Wi-Fi. That system, I can guarantee, will not work unless the antennas are spatially wide apart and you have 70 or 80 dB of isolation, like I showed earlier. So this kind of chart helps you walk through the whole system. Is does the V2X system need to coexist with the 5 GHz with the Wi-Fi? If the answer is no, then you don't worry about coexistence. But if the answer is yes, then the next question to answer, like I said earlier, is what is the level of isolation that you would have between the V2X and the Wi-Fi system? Because that antenna isolation will tell you what to do next. If you have 70, 80 dB of isolation, regardless whether you need coexistence or not, you don't need to worry about it because the system will handle it. However, if the antenna V2X to Wi-Fi antenna isolation is less than 70 dB, then you would need some more work. You would need to do a system analysis to understand the amount of descents your V2X receiver might see. And we have products that enable coexistence. That is, the bandpass filter is right here, the 2200Q, and the notch filter, the V2X notch filter, which will go in the Wi-Fi system we talked about, these two filters together will bulletproof your V2X system against Wi-Fi interferences. Now, a different case could be that, does the V2X system need to coexist with electronic toll collection? This is again a question. If you're a V2X system designer, do you have coexistence with Wi-Fi? Do you have coexistence with ETC? This is the question you should ask. And if the answer is no, don't need to worry about it. If the answer is yes, then we do have products which enable coexistence and between ETC and V2X systems, like I showed earlier. If you are designing a Wi-Fi system, a dual band or single band Wi-Fi system, the question, the first question would be that, does this Wi-Fi system need to coexist with the NAD? This is a question. If you're designing that, you've got to ask the car OEM, is there going to be a NAD? And if so, what is the regional configuration of the NAD? Would it need to coexist with band 40, band 7, band 41? If the answer is yes, then you do need a 2.4 gigahertz coexist filter. And we have multiple products, but our latest and greatest is the QPQ2254Q, which enables coexistence between 2.4 gigahertz and the LTE bands. Now, if you're designing a Wi-Fi system, you're a Wi-Fi designer. On this side, you are a V2X designer. If you're a Wi-Fi system designer, the question to ask is, do you need to coexist with V2X? And if the answer is yes, then you go back and walk through this full flow chart. So I thought this was a pretty nifty tool that should help you identify, ask the right questions. And just to summarize it all together, like I said earlier, we have been working with car OEMs and tier 1s and tier 2 module makers. And what we have learned is working closely with our suppliers is that module makers is that there are a lot of system challenges. And understanding those system challenges has helped us come up with unique solutions that we talked about today. The filters for the V2X system, the filters for the Wi-Fi system, the filters for the electronic toll collection systems, and all these coexistence situations require careful attention, asking the right question. So please use my slides. If you find this information useful, and if you have any questions, you can reach out to me. My contact information is here, and we can have further dialogue discussion about it. Of course, I would welcome you all to explore our resource library. We have Qorvo Design Hub, which has lots of articles and papers and published blogs and everything. There are block diagrams, there are design tools, which you could use as well. And that said, I would like to pass it back on to Rich.
Thank you very much, Ali. Very, very informative. I know I certainly learned a lot from this. I have to say, though, if you do need to borrow any cassettes, you let me know, because I have a whole cabinet full of cassettes for you.
I will keep that in mind.
So,
yeah.
And the fact that the cigarette lighter came before the radio, I guess we have to give people a pass, because they didn't even know that cigarettes were dangerous in 1925. But
True.
But I digress. Okay. We have some questions here from the audience. We will get to as many as we can. I encourage you out there, just keep asking, and we're going to go up until the top of the hour. And then if we don't answer them, somebody from Qorvo will get back to you after we're done here. Okay, ready, Ellie?
I'm ready.
Okay. Does Qorvo have other products to support V2X applications?
Yes, we do. We have a full lineup of products. We have the V2X FEM. We have the switching components. We have the filters we talked about today, the different types of filters. We have gain blocks. And all of these, we have a full lineup of filters of the whole product portfolio for V2X. All these products are in mass production, and they are AEC-Q grade 2 qualified, which is important for shark fin applications, especially for active antennas. You need these products to be grade 2. So the answer is yes. We have a full lineup of a V2X portfolio. By the way, this portfolio has been tested and proven. It is we have close working relationship with our chipset providers for V2X, and they have tested and validated the full solution on their with their chipset to make sure it works properly.
Would you talk a little bit about that testing process, because that's significant?
Yeah, absolutely. So we work with our chipset providers. Like I said, we work with them while we are developing the product. They get to see the first samples. They plug it into their system, lay out the boards, and there is a lot. It's a very iterative process. Like most of the RF designers know that it's not a slam dunk. And the problem here is that, if you have designed, my background is electrical engineering, so I used to be a hands-on designer. It was tricky to work with systems at 2 gigahertz. This is 6 gigahertz. At this high frequency, the parasitics matter a lot. The matching and optimization, every little bit, it looks like a lot at 6 gigahertz. So the matching and optimization process is not just one board. It's iterative process. Now you have this filter that I talked about, the bandpass filter, that is based on our BAW technology. That filter, in order to get the performance that we show in our data sheet, you need to design that filter, lay out that filter properly. You need to have certain kind of via structures underneath it. If you don't present the right inductances to this filter, the out of band performance will be out of whack. So the importance of testing and validation is that someone has already done the work for you. Now all you have to do is take that system and replicate it on your side. It would save you a lot of R&D effort and iterative process. We at Qorvo, our applications team, has taken the 6 component lineup and have a systems board with well optimized performance just to demonstrate the RF in and RF out of everything. And of course, this information is, if you're working with our components, we will provide you all the help in matching optimization, schematic reviews, and layout reviews, and make sure that you get to your finish line in the fastest possible time frame. Important thing is that this whole solution set has not been it's been time tested, not just by system providers, the chipset providers, but also today multiple customers are ramping this solution in on their system on their end. So
Okay. Next question. Are these filters AEC-Q qualified? If not, will they be?
all the V2X components that I showed today are AEC-Q grade 2 qualified. In some cases, we do decide to grade 2 or grade 3 qualify grade 3 instead of grade 2, just because maybe if it's a filter, it's going to be dependent on the temperature dependency is there. It's just the physics of the device. So in some cases we have grade 3, but I would say they're all AEC-Q qualified. It's important for automotive applications. It's table stakes to have AEC-Q grade qualification.
Okay. Along those same lines, are these filters chipset dependent? Which I guess is processor dependent?
No, not processor. Processor is more signaling. It's more on the digital side of things. Chipset is more on the RF side of things. But no, they're not chipset dependent. So, it is really a V2X system requirement that these filters are designed to. It's more RF dependent.
Okay. The next one is a little longer. Is the V2X Coexist filter QPQ 2200Q and the V2X notch filter needed for DSRC or CV2X systems? Did you get all that?
Yeah, I got all that. Well, good question. Okay. Great question. So regardless of V2X system, when I use the term V2X, that could imply either CV2X or DSRC. And all the solutions that I showed today, if you remember the spectrum plot that I showed for the V2X, it's the same spectrum we are talking about. Whether you're on the right side of the spectrum or left side of the spectrum, it's 5855 to 5925. And whether it's CV2X or DSRC, you're still working with the same piece of the spectrum. So you need to address it with the exact same filters. I hope that addresses your question.
I hope so too. Okay, let's see. With regards to electronic toll collection, how is this being done today? And are there other ways to address V2X coexistence with ETC, electronic toll collection?
Yes, great question. So today, the ETC radio is dependent on the mapping software. And the mapping software has to tell, when you approach a toll plaza, and the ETC radio, the little radio in your car, wakes up and does the tolling transaction. So it's dependent on the mapping software. But if you remember the spectrum emissions plot that I was sharing that if you had a V2X radio in the car, and if the V2X radio is on at full power, the ETC radio will not be able to see itself. So it's mapping software dependent. The way you mitigate it is 2 ways. You can do it through software. You could possibly, I've talked to some folks, and I've learned that you could possibly maybe back off V2X power in order to enable coexistence of V2X with ETC. But if you were to back off power, remember the use cases. If you are, these are safety related use cases, backing off power, I'm not sure. I'm not a systems expert, but I'm not sure that is the right thing to do, because you back off power for a V2X system, which is driving, which is, on that link, you are passing on all the safety related information, the time critical information. You really want to back off power even for a short amount of time for doing a tolling transaction. And I think really a hardware solution would be, or maybe a combination solution would be the right solution for addressing coexistence. But yeah, I mean, there's hardware solution and a software solution.
Okay. We only have a minute or two left. I got one more, and I don't know if this is a question that we can do in a minute or two. However, I'll ask it anyway. Do you have any recommendations on placement location of the toll collection filters?
Yeah, the placement location would be, there are two places you can place them. One is before the V2X FEM on the TCU side, or you can place it before the V2X FEM on the active antenna side. You don't need it both places, one or the other.
Well, that was easy. Where would somebody get more information about the filters?
Talk to me.
There you go. And your contact information was in that last slide. As we said earlier, download those slides by clicking on the handouts widget at the bottom of your display. We are out of time. That was very well done, Ali. I appreciate you taking the time to educate the audience. A reminder that all Open Systems Media webcasts are copyrighted. It may not be recorded without prior permission. Another thank you to all the sponsors of the Automotive Technologies Virtual Conference. That would be Qorvo, IAR Systems, Texas Instruments, AD-Link Technologies, and Imagination Technologies. These presentations are all available in an on-demand version, not just the 3 live ones that we presented today, but all the ones that were pre-recorded. There's between 15 and 20 presentations in total, and they cover ADAS, autonomous drive, electric vehicles and powertrain, in-vehicle infotainment, and safety and security. So please check them out. They will be alive for a while, for 6 months or so. So you can refer back to them whenever you want. So a big thank you to Ali for doing a great job, and certainly to you, the audience, because we can't do these things without you. I hope you have a great day, and we'll see you next time.